Now, we're going to get into three-dimensional rigid body statics. And I have to start by talking about three-dimensional joints. All right, so remember when I started talking about two-dimensional joints, I said, so remember, a 2D rigid body in space has 3 degrees of freedom. Has 3 degrees of freedom. Two translational, and 1 rotational. And the number of variables that a joint introduced into Newton's laws all came from how many of these degrees of freedom it eliminates. Okay. So now let's think about a 3D rigid body in space. Okay, so I'm going to draw this sort of block thing. And I'm going to draw a bunch of axes. So there's one that way. There's one that way. And then one that way. Okay. And let's think about the degrees of freedom that this object has. Okay, well, the one that makes total sense, that's easy to imagine, is that now we have another axis of translation, right? You can translate along the positive and negative x-axis. You can translate along the positive and negative y-axis, just like you could in 2D. But now we have a three-dimensional space, so you can also translate along the positive or negative z-axis, right? So there's translation along 3 axes. But now think about the rotations. Before we only had 1 because you had to stay in the plane, but now you can rotate around that axis, and you can rotate around that axis, and you can rotate around that axis. Okay, so now you can have rotation around 3 different axes. And so altogether, this says that there's 6 total degrees of freedom. And the loads that are applied to a body by a joint, just like they were in 2D, are going to be determined by which of these degrees of freedom they eliminate. So each joint type eliminates, some set of these 6 degrees of freedom. Okay, so now I'm going to go through, just like I did before in 2D, I separated things into categories where a category introduced the same number of variables, the same number of loads. Again, the way it's going to work is if a translation is disallowed, it's going to be disallowed by a force along that axis. And if a rotation is disallowed, that's going to be done by a couple about that axis. Okay. Forces now are going to be given, a force vector is going to be shown like it was before, an arrow. But a couple vector is going to be shown by the direction of the vector, but the arrow is the arrow is going to have 2 heads on it. Okay. Okay, so I'm going to start with joint category 1. So these are the joints that apply a force with a known direction how many variables do you need to represent a force with a known direction? So for a force vector, if you didn't know the direction, you'd need all 3 components, right? If you do know the direction, though, you know a unit vector, and you can just think of that force as a number times a unit vector. So there's only 1 variable you need in this case. So to apply a force with a known direction, it brings 1 variable into the equations, into Newton's laws. And there are 2 of these that do that. The first one is a frictionless contact. So I'm not really going to try to draw this in 3-dimensionally, but it works the same way as it does in 2D. The direction is always perpendicular to the surface of contact. So if this is body 1 and this is body 2, then a free body diagram of body 1 make it look a little more like the one over here. Okay, is going to be perpendicular to this surface of contact. So it's going to be like that. So that's 90 degrees, and we call this, N or whatever. Right. Yep. And the second type in 3D is a roller. So one thing, though, that you have to be careful with now in 3D is Now we're talking about rollers that can move freely in any direction. Yes, question? The opposite. Yep, that's right. So a roller, but we're talking about like a ball roller, not a wheel. Because a wheel has a preferred direction. So in this case, we're talking about something like this. So if this is body one, again, free body diagram. If this is the surface, the force is a normal force perpendicular to the surface. Okay, so those are the two types of joints that bring one variable into Newton's laws. What about the directions? Could you get negative values for these ends, either of them or both of them? No, you could not, because a negative value of n would mean that the ground is like pulling down on it. Okay, so notice you have to get positive numbers for these. N must be positive for both of these. It could be 0, yeah. Yep.
So what's the difference between a ball roller and a frictionless contact?
There's no mathematical difference. It's just like, you know, if you're like in a, you're looking at a picture of a setup, or you're in a room looking at things, you just have to recognize that mathematically you treat them the same, you know. Okay, so now joint category 2. So there's only one of these, and I think actually there's only going to be one of everything from now on. And we're going to go all the way through all of these different numbers of variables that are introduced. What's the most number of variables that we're going to see? 6, exactly. 1 for each degree of freedom. So we're going to have a type for 2, 3, 4, 5, 6. So this applies force components in 2 directions. And introduces 2 variables into the equation. Into Newton's laws. And the only joint in this category is a wheel with a preferred direction. So that would look like this. Where the preferred direction is this way. Okay. And a free body diagram. If this is the direction that it's free to roll, what are the directions of the force that this applies? Well, it doesn't apply any force along the path that it can follow. It applies one perpendicular this way, and one perpendicular this way. So this is perpendicular, and this is perpendicular. So one of these is a normal force, and then this other one is like a friction force, or if it could be on a rail or something if it's like a train. But something is applying a force that keeps it from leaving that path. Did I draw this right? That sort of looks like an MC Escher drawing, I think. Here's what we want. Any questions about that one? Right. Yep. Yeah, wheels we're always going to represent as frictionless. We'll talk a little bit about some kinds of wheel friction, I guess, right at the end. Okay, so now joint category 3. Well, it's frictionless along its path, but the friction keeps it on the path. Okay. I don't have a good demonstration of this. But... Okay, so now, what? Yeah, we'll be solving for F and N. Yep. So those are the two variables that it introduces. Joint category 3. Applies a force vector with a totally unknown direction. And so if you have a force vector with unknown direction, that means that it prevents translation anywhere, okay? So all translation is eliminated. We haven't had any couples yet, which means for all of these, rotation is possible around any axis. Okay, so this introduces 3 variables. And the joint in this category is a ball and socket joint. So you have one piece like that, one piece like that. And a free body diagram of that part 1. Has 3 force components. And you can just represent it as like the force on body 1 by body 2. If this is body 2. Okay, so here's a ball and socket joint. We have to pretend there's no friction, but there's a lot of friction. But let's think about the translations. Okay, so imagine this one's fixed. The thicker one is fixed. Is there any axis where I can translate the center of that ball out of that point? No, so all translation's fixed. So it makes sense that that there's a full force vector. But now let's think about the rotations. Okay, so let's just arbitrarily, let's say the x-axis is this way. Okay, can I rotate the top around an axis that way? Yeah, so that would be this. Okay, and let's say that the y-axis is this way. Can I rotate this around the y-axis? Yeah, that's like this. Okay. And then can I rotate it about the z-axis, which is like this? Yeah, that would be like, supposed to be able to. That'd be if I like grind it like that, you know? So that's why, so thinking about it that way, you can tell that there's a full force vector and no components of a couple. Okay. This is pretty much how like hip joints and shoulder joints work. Okay. Now here is the trickiest one to deal with. Joint category 4. So this is the trickiest one to use. You got to think about this one each time. And the reason is that you don't always treat it the same way. This introduces, let me say, it's up to, or it introduces up to, four variables into Newton's laws. And here's how it breaks down. There are 2 force components. And those are always there. And then there are 2 couple components. That are there only when not used as a coaxial pair. Okay, I just made up that phrase, but a pair that has the same axis. That sounds like an official thing. It's not. Okay, so let me show you how that works. So this is a pin joint without thrust. And it looks something like this. So you have one object here. Connected to another body here. And they're connected by a pin that goes through. Okay. You with me on this? And I'm going to call the axes, so we'll have one axis this way, one axis this way, so I'll call this X, this one's Y, that means this one's Z. I'll call this one body 1 and this one body 2. And let's think about the motions that are allowed here. So this one has the thing that I'm thinking of is member 1 is this really skinny piece on top, okay? And you can see the pin here is free to slide along its axis. So like that's the Z axis in this picture. It's sliding along the Z axis when it does this, okay? And let's think about translations and rotations. So if I position it like this, can this top piece translate along the x-axis, forward or back? No. Can it translate up or down along the y-axis? Not the y-axis, okay? But it can translate back and forth along the z-axis. So what directions are the two forces going to be applied? Yeah, so there's going to be one force in the x direction, one in the y direction. And now let's think about the rotations. Can this top piece rotate around the x-axis? Nope, that would be this, like, tipping this way or that way. Okay, can you do that? Can it rotate about the y-axis? So that would be me twisting it like a screwdriver. No. Can it rotate about the z-axis? Yes, it can do that. That's the motion that it's kind of made for, you know. So a free body diagram of member 1 has a force component in the direction of x. So I'll call that the fx component. It has a force component that better not be gone. Oh. Okay. Free body diagram of member 1. Okay, so we got a force component along the x-axis. A force component along the y-axis. And those two are perpendicular to each other. ahead, give me back the first one. Okay, free body, I'm gonna try it one more time. Free body diagram of body 1. Okay, there's a force vector in the x direction. A force vector in the y direction. None in the z direction. These two are perpendicular to each other. And now what about the couples? Well, we said that there was a couple preventing it from rotating about x. So I'll call that a couple component mx. And there was a couple preventing it from rotating about y. So there'll be an my. Okay. When don't you need the couples? So when don't you use the two couples? So in a case like this, where you have two of these pin joints, you can think of these as hinges that share the same axis. Okay, so these are two pins, two pin joints with the same axis. So now let's go to joint category 5 that works the same. So joint category 5 is just like the pin joint without thrust. But now thrust is applied, is generated. So this joint applies up to applies, that's not the right word. What did I say before? Joint, sorry. So up to 5 variables are added to Newton's laws. And this joint looks like, so this is a pin joint with thrust. The most likely way that you would see this is like a pin joint with brackets on both sides. Okay. You follow the idea of that? Oh, dang it. Okay, I'm going to leave it alone. And so if this coordinate system, so like say you have the z-axis going along the pin, and the y-axis up, and the x-axis this way. And let's say this is body 1. Then a free body diagram of body 1 looks like this. Well, so let's think about how this looks, and then I'll draw the loads in here. So here's the pin joint I have that applies thrust, and you can maybe see over on your left side, there's little flanges here that prevent this from sliding. Okay. So that's how that thrust is applied. On this one, I could slide it back and forth. There's no force that keeps it from sliding. But here, that can't happen. Okay. And so let's think first about translations. So can I translate this joint that way and that way? No. So there's a force in that direction. How about up and down? No. And now we also can't translate along that pin. Okay. So there's a full unknown force vector applied. There's no translation that's allowed. Okay, so the first thing I'm going to do is draw in those forces, draw in that force vector. So it's like this, and I'll call that, the force F. That's the force on body 1 by body 2. And now let's think about rotations. Can I rotate it like this? No. Can I rotate it like twist it? No. But I can still do this. That's what it's for. And so there's no couple applied about the z-axis, but there is about x and y. And again, with these, I'm going to put them in parentheses. I'll draw it here. So we have a couple in that direction, a couple in that direction, because those are the rotations that aren't allowed. But I'm going to put them in parentheses because those are the ones that aren't always there. So my, and here's mx. Okay. They are only there if there's not a second pin joint along the same axis. Okay. And again, like in the first case, all right, they'll apply those couples, but you don't want your kids hanging on it, Yes?
Can you draw that just with your double arrow, single arrow, or did you have to draw like?
Say it again. Can you draw?
Like, can you just, instead of having a forced arrow, can you just draw a double arrow going up?
No, because those are only couples. The double arrows mean a couple. So you have to also show that there's a force. Okay, so if there are two pin joints, sharing that axis, then don't include the couples. Okay, so pin joints with thrust and without thrust work the same way. It's just that one has a force along the z-axis. And I keep, all of these, what I'm saying, couples around the x-axis and y-axis and z-axis, that all just depends on this arbitrary coordinate system that I have here. So you're going to have to do problems where it's not the z-axis that pin can rotate around. You're just going to have to, visualize it in each individual problem. How does this thing rotate? This might be the x-axis in some problems, or the y-axis in some problems. So you just have to be able to visualize how are the degrees of freedom restricted by the joint. Find the places where it can't translate or it can't rotate. That's where the loads are applied. Okay? And then the last one is easy. So that's joint category 5. So now that was joint category 5. So now we're on 6. So joint category 6. This introduces 6 variables into Newton's laws. And the only joint like this is a fixed joint. Sometimes it's called a weld joint. And so if you have, something that's just rigidly connected to another body. So this is, let's call this body 1. And it doesn't matter what your coordinate system is, but let's say we have the y-axis that way, the x-axis this way, and that means the z-axis is this way. Then a free body diagram of body 1. There's a full unknown force vector because no translations are allowed. So this is the force on 1/2. And then there's a full couple vector because no rotations are allowed. So now there's also a couple component in each of these 2 directions. And you can call that the couple vector on 1/2. Actually, now I realize I didn't use that subscript up above. So let's go back here and write well, I don't know. You can write this in the margins or whatever, but this could be represented as M on 1/2 Y component and M on 1/2 X component. You can use that double subscript notation. The reason you use that double subscript notation is because Newton's third law means if you switch those subscripts, you multiply by -1, and it works with couples too, which makes sense because a couple is just 2 forces. So if you switch the subscripts, you're just changing the directions of both of those 2 forces. It changes the direction of the moment. Okay, Any questions about any of the joints? All right, let's do a 3D problem. Bless you. Yeah. Okay, so let's say this is like a, how big is this? Yeah, it's sort of like a sign, like on the roof of a restaurant or something. So it's this rectangular shape. Um, and right at the top on the back, it's connected to the wall by a ball and socket joint. That's supposed to be like a little bracket holding the ball and socket joint. Yeah, well, this is what we got. And then there's two cables connected, one here and one here. And the one at the end, maybe that's right, goes to the wall over here. And the one a little closer to the middle goes to the wall up here. Okay, so let's start doing some dimensions. Here's the center of mass, the center of this sign. Okay, that's terrible. Let's see. So what do we know about dimensions? We know that it's 1/2 meter from the end to where that second cable is applied. And it's 2 meters from that line back to the back. And to get from, so both of these cables connect to the wall. So to get from the pin joint to this point here, I'll call that the point B. We have, this distance is 2 meters. And this distance is 1.5 meters. Okay, you're gonna have to kind of suspend disbelief for some of these dimensions. And then on the other side, it is 1 meter from here to here. And then that's also 1 meter. Okay, so you're like, hold on. You're telling me that this is only 2/3 as big as this? Okay, well, you're looking at this for like 20 grams or something. This is the point A. Okay. And the coordinate system we're going to use as the x-axis going, so the origin is at that pin joint. The x-axis goes this way. The y-axis goes up. And that means that the z-axis has to go this way. The mass of this sign is 50 kilograms. And we want to calculate the reactions, the reactions from the pin joint. Not pin, it's a ball and socket joint. Reactions from the ball and socket joint to the sign, and the tensions in those two cables. Okay. Is everyone sort of with me on this? Well, on three-dimensional problems, I think probably the first thing you want to do is just figure out the coordinates of all these points, because it's not really very useful anymore to use cosine and sine to figure out the directions of unit vectors. You know what I mean? So let's just go based on this origin and this coordinate system, figure out the coordinates of the center, and that's where the weight's going to be applied. This point, A and B. Yeah, and that's all we need. And then from there, we'll just be able to subtract vectors from each other, normalize those, that kind of thing. Yeah. The height of the sign. I guess we don't, because the line of action of the weight force is up and down. So, and you can move that force along the line of action. Okay, so let's draw a free body diagram. These can be a little tricky in 3D. So I'm just going to draw it like something with no thickness. Okay, and what are the loads that are applied? There's a weight force that's equal to 50 times 9.81, so 490.5. And then there are two cable forces. One goes this way, I'll call that TA. And then the one at the end goes this way, I'll call that TB. And then the last thing we have is a ball and socket joint. What kind of loads are applied by a ball and socket joint? So think about what degrees of freedom are eliminated by a ball and socket joint. I don't have the thing with me, but that's right, no translation, right? But any kind of rotation is possible. So there's not going to be any couples. There's just going to be three force components, okay? So we have that, and that, and that. And I'll just call this the reaction force R. Okay, how many equations are Newton's laws going to give us? 6 total, yep. And how many variables do we have? 5 in this case. And so this is something that's going to be pretty common in 3 dimensions that we really never see in 2-dimensional stuff. And that is that sometimes, not all, pretty often, not all of the 6 equations are going to be useful, you know? And so I think what we're going to see, I don't really remember this one, but what we're most likely going to see is that one of our 6 equations, when you write it out, just ends up being 0 equals 0. And so we're going to have actually only 5 useful equations to solve for 5 variables. Okay. So let's start writing out this table. Row vector, force vector, and moment. Oh no, I'm sorry, I said first let's come up with all those coordinates. We didn't do that. Okay, so first, the ball and socket joint is the origin. What about A? How do you get to that point A? Yeah, so x is 0, yep. Y is 1, positive 1, and Z is positive 1. You see that? So that point A, the coordinates are 0, 1, 1. The point B, x is 0 again. We have to go in positive y direction 1.5, and then in the negative z direction 2. So that's going to be 0, 1.5, 2, negative 2. So B is 0, 1.5, negative 2. Then the center of mass, well, let's label all these points. So we got A, B, let's call this C, D, and then the center of mass, E. So C, so you go 2 meters in the positive x direction, and 0 in the y direction and 0 in the z direction. It works the same way to get to D. You just go 2.5 in the positive x instead of 2. And then the center of mass at E, yeah, in the positive x direction, you go, the whole thing is 2.5 meters. We're going to the midpoint, so 1.25. For y, it doesn't matter because the weight force is vertical. And then for z, it's 0. So this 0 here, it's not really at 0y, but that's like we just moved that force along its line of action. Yes, right. Any questions about finding those? And for this one, now that we have all these, let's choose the about point at the origin. That's a good place for it anyways, because that's where we have the most unknown force components. Okay, so now I'll set up the table. Row, force, moment. I'll do that force R first. So the R vector goes from the about point to where the force is applied. What is it for R? 0, yep. We have to do everything in 3 dimensions now. The force vector is Rx. ry, rz. And the moment is 0, 0, 0. We do, yeah, because, so, you know, our 6 equations are going to come from the 3 components of the force equation and the 3 components of the moment equation. Okay, so now let's go to the weight force. Those 2 cable forces are going to really be a pain. Let's save those for the end. So the weight force, the row vector, well, since we chose, you know, anytime your about point is the origin, your row vector is just the coordinates where the force is applied. Does that make sense? Because the row vector is just a vector that goes from your about point to where the force is applied. Okay. So the row vector is just going to be 1.2500. The force is 0, negative 490.50. And that cross product is 0, 0, negative 613.13. Okay, so now we're getting to those 2 cable forces. So the first one, let's do that force TA. Well, the row vector, I mean, again, because the about point is at the origin, is just going to be the coordinates of A. So that's 0, 1, 1. No, it's not. That's C. Yes, thank you. Okay, 2, 0, 0. And then the force vector, so how are we going to get the force vector? This is where it gets to be a pain. Yeah, so we're going to have to get the unit vector that goes from C to A, and then multiply that by this variable TA. Okay, so the unit vector, so let's do that for, you know, cable A first. So first, let's get a vector that's in the right direction. So our vector U is going to be, so to get a vector that goes from C to A, that's going to be the coordinates of A minus the coordinates of C. So 0, 1, 1 minus 2, 0, 0. So you get this vector negative 2, 1, 1. And now we have to divide that by its magnitude. And so a unit vector in that direction, if you're lucky, your calculator does that for you, is negative 0.816, positive 0.408, positive 0.408. Okay, and so that force then is this unit vector times the variable TA, so negative 0.816 TA, positive 0.408 TA, positive 0.408 TA. Okay, so now take the cross product of these two. And you get 0 for x, negative 0.816 TA for y, and positive 0.816 TA for z. And then the last force is the cable B. Okay, so now TB. The row vector is 2.500. And now we have to do the unit vector thing again for cable B. First, a vector that's in the direction of this cable. So, we want our unit vector to go from B to B. So we're going to do that as the coordinates of B minus the coordinates of B, and then normalize it. So this vector U, before we get it as a unit vector, is 0, 1.5, negative 2. Minus 2.500. And so you get the vector negative 2.5, 1.5, negative 2. And then a unit vector in that direction, figure out the magnitude, divide every component by the magnitude, and you get negative 0.707, positive 0.424, and negative 0.566. So the force vector is that unit vector times TB. So negative 0.707 TB, positive 0.424 TB, and negative 0.566 TB. And now take the cross product of those two vectors, and you get 0 for x, 1.42 TB for y, and 1.06 TB for z. Okay, so our three equations, our six equations, are 3 for forces and 3 for moments, are going to be, we're going to add up all the x components of forces and set it equal to 0. Add up all the y components of forces, set it equal to 0, z components. And then we'll do the same thing with each component of the moment. I said at the start, we only have 5 variables that we're solving for. We normally, we would expect to get 6 equations. What's the equation here that isn't going to be useful? Can you tell from looking at this? Yeah, the x component of the moment equation just says 0 equals 0. So I'm going to cross that out. That's almost always true in problems that are given in textbooks. Like any problems that I looked up in textbooks are that way, because they don't use reduced row echelon form, so they have to set them up in a way that you can do it with substitution. That usually means like reducing the variables somewhat, but okay, so the equations are Newton's second law says Rx, Ry, Rz plus 0, negative 490.50 plus negative 0.816 TA, positive 0.408 TA, positive 0.408 TA, plus negative 0.707 TB, positive 0.424 TB, and negative 0.566 TB is equal to 0 vector. And then the moment equation says, I'm going to write out all three components, but 0, 0, negative 613.13 plus 0, negative 0.816 TA, positive 0.816 TA, plus 0, 1.42 TB, 1.06 TB, is equal to the 0 vector. And, you know, this X equation, you can see, doesn't help. And so we have 5 equations for 5 variables. There's equation 1, 2, 3, 4, 5. And if you do this with reduced echelon form, you get that the R vector is 527.5, 210.2, and negative 35.1. Those are all newtons. And the tension in cable A is 429.6 newtons. And the tension in cable B is 247.7 newtons. And so based on those calculations, you could maybe, you know, make sure that you had a thicker cable in that position, cable TA, cable A, and you could use less material in the cable for B.